So, welcome to today's lecture. If you recall, in the previous lecture we had started looking at geometric representation of the plane. So, let me explain that a bit more, so that we have a good idea about. So, here is r cross r. So, r 2. So, this is the Cartesian product of the set of real numbers with itself. So, as a set, R 2 is nothing but x comma y, where x and y both belong to R. So, this is a set of all ordered pairs. What is the geometric representation of this? We take this as the plane, okay, this paper as the plane, and on the plane we draw two lines, one vertical, another horizontal. So, this we mark it with arrows. You can think of this as a copy of the real line starting at 0. So, on this side it will be 1, 2, 3 and so on. On this side minus 1, minus 2, minus 3 and so on. The vertical also is a copy of the real line, where upside is positive. So, this is 1, this is 2, this is 3 and so on, and the bottom side is minus 1, minus 2, minus 3 and so on. So, we have made two copies of the real line, one is horizontal, other is vertical, and both are perpendicular to each other. What we want to do is every point, every ordered pair x comma y belonging to R 2, we want to associate to it a point P in this plane. So, this is my plane, right, a point P. So, how do we locate the point P? When we have the ordered pair x comma y, we would look at x, okay, and then move x units along the horizontal axis. So, this is what is called the x axis, horizontal, and the vertical one is called the y axis. So, x units along the horizontal line. So, we go, if x is positive we will go this side, if x is negative we will go this side. So, somewhere x comes, x units. So, this is x, right. In the ordered pair for y, we have got the number y. So, what we will do is again look at whether y is positive or negative. If it is positive, we go up, if y is negative, we go down, and that many units. So, let us say y is positive. So, we go up, right, and reach a point. So, this is y units. So, we reach a point, and this point is called P. So, P, we say P has got coordinates x comma y. That means x units you move on the x along x axis and then go parallel to y axis, and distance is y. So, that is, so from here R 2 to plane we have got a map. This map is a correspondence actually. Why it is a correspondence? Now, suppose I am given any point P, right, it has got coordinates alpha beta, say. Okay. So, what does that mean? That means, if I move alpha, alpha is along x axis, beta is along y axis. So, this distance will be beta and this distance will be alpha, right. So, to reach this point I have to move alpha units and then beta units I get. So, this points gets associated with alpha comma beta ordered pair belonging to R 2. So, what we are saying is every point in the plane gets associated with an ordered pair, and every ordered pair gives rise to a point. So, this is the set theoretic representation as a set, and this is the geometric representation of the plane as set of points. So, we will be using this to represent the graph of a function. So, let us take a graph of a function. So, f is a function from a set x which is to a set y, right. Here we have got x is a subset of R. So, let us be more precise, f is from x a subset of R to y which is also a subset of R. So, what is graph of f? Graph of f is nothing but the set of ordered pairs x comma f of x, x belonging to x, right. That is a subset of R cross R, that is R 2. How do we represent it graphically? So, as before, we take our graphic representation. So, this is x axis, this is y axis, this is x axis. So, what we do? You take any point x comma f x. So, take x, this is x units, okay. And what we do? From now we move how many units? Y, y is f of x. So, go parallel to say go parallel, you will get f of x. So, this is f of x, this height, and this is x. So, you get a point. So, locate all such points. So, given any point x, locate maybe f of x is here, maybe f of x is for this point x, for this point x, f of x may be somewhere here, right. So, these dots will represent the graph of the function g of graph of the function f. So, these dots are the for this x, f of x could be probably here. So, these dots represent the graph of the function f. So, that is what geometric representation of the graph means. So, here is an observation that a graph normally will give you some kind of a curve in the plane. A graph will give you some kind of a curve in the plane, right. But every curve in the plane need not be the graph of a function. This is slightly a subtle point, we will see it soon what does that mean. So, for example, let us look at a picture and try to see. Let us say this is the axis and this is the graph f of x. So, that is my graph. So, here is y, here is x. So, for a point x, what is f of x? So, this is f of x, because what are the coordinates of this point? X comma f of x. So, this is also I think this is the right time to also say that how do you interpret a graph. So, we are given some graph. Okay. What does that mean? That means, if I take at any point x a vertical line, then wherever it cuts it, that is the value of x. So, at every x, this is f of x. Okay. At every point x, this point is f of x, right. And you see in this picture, whenever I am drawing a line at every point x, a horizontal line that cuts the graph only at one point. So, this line that I have drawn is the graph of a function. It is a relation which is a function. Let me draw another graph, another curve, and look at what is happening. So, let us draw another picture and let us look at f of x. Can I say that this curve is the graph of a function f? So, let us call this curve as this curve. So, let us is this the graph of a function. So, this is my x, this is my y, right. So, if it is the graph of a function, then it is from R to R, right, because this is how I have looked at, this is a real line, this is 0, 0 and so on. Okay. Now, for a graph, what is the, it is a subset of the plane, this is R 2. So, it is a relation. So, this points x y on this blue curve are related to each other because they are on the curve. Now, the question is, can I say this is the graph of a function? Well, to be the graph of a function, what is the property we want? For every x belonging to R, x should go to unique y equal to f of x. And how do we find? For any point x, what is f of x? For x, so I draw a vertical line. So, this is my f of x, this height, right. So, this is my f of x. But if I go, for example, here, I take a point x and draw a vertical line, it intersects at more than one point. So, that means what? At this point, possibly this could be the value of the function, this could be the value of the function, this could be the value of the function. That means, these 3 points, right, if I look at corresponding points in y. So, this is one point, this is the second point and this is the third point. So, these 3 points on y are related with the same point x. That means, this condition is violated. X is not associated with a unique point y, it is associated with more than one point. So, this blue curve is not the graph of a function. So, a test for a curve to be the graph of a function is that every vertical line should intersect at the most at one point. So, this is what we are saying, that a curve in the plane such that every vertical line will intersect the curve at the most one will be the graph of a function. For example, here, so this, if I take any point x and move it this line around, then it intersects only once. So, this is the, this blue line is the graph, but what we saw just now on paper, that is not the graph of a function. So, not every picture in a plane is the graph of a function, right. So, the test is the vertical line test, every vertical line should not intersect in more than one point, then it is the graph of a function. I think this is the right time also to look at what is called 1 and onto function. So, let us look at something. So, let us say f is a function from x, which is again a subset of R, to y, which is a subset of R. X goes to f of x, which is normally denoted by y. What is called a 1 function? Intuitively, the real line, but let us imagine this is x and this is y. As such, they are parts of real line, but anyway, let us, for the understanding, let us say this is x. Possibly, a point x goes to a value f of x, right. So, let us call x1 goes to a value of x1 and another x2 also goes to some value f of x2, but it so happens x1 and are equal to x2. So, if f is such that f of x1 is equal to f of x2 for x1 not equal to x2, that means different points go to same value, then we say f is not 1, it is not 1, because more than one value goes into the same value, right. So, let us look at some examples of this. So, let us look at a function f from real line to real line, where f of x is equal to x square, right, for every x belonging to R. Okay. Now, can I say that if f of x 1 is equal to f of x 2, does this imply that x 1 is equal to x 2? Well, let us analyze. F of x 1 equal to f of x 2, what does it imply? This implies, by the given formula from here, x 1 square is equal to x 2 square. Does this imply x 1 is equal to x 2? Well, we all know in general. For example, if I look at x 1 is equal to 2, x 2 equal to minus 2, then x 1 square is equal to 4, which is same as minus x 2 square. So, what does this mean? That means that this function is not 1 1. So, let us write this as an example of, so f of x equal to x square, x belonging to R is not 1 1, is not a 1 1 function. Okay, let us look at geometrically what does it mean. Let us look at a function f from R to R, which you have already come across. Okay, f of x is equal to mod x. Okay. Once again, it is not 1 1. Okay. Why it is not 1 1? For example, mod of x 1 equal to mod of x 2 does not imply x 1 is equal to x 2. It only implies that x 1 is equal to plus minus of x 2. So, this is not a 1 1 function, right. Let us also define what is called another property of functions. So, let us say f is a function from x from R to R. So, y is equal to f of x. Right. Now, recall we defined what is called the range of the function to be equal to all y such that y is equal to f of x for some x belonging to the domain. So, in general, we saw examples. Range f is a subset of the codomain. Here it is R, that is a codomain, right. So, in case range f is equal to codomain, f we say f is onto, f is a onto function. A function f which is both one one and onto is called a bijective function. Before we give examples of 1 1 and onto functions, more examples of it which you are able to visualize, let us draw graphs of some easy functions. So, let us look at a function which is called the constant function. Normally, functions are specified by formulas. So, let us look at a function, say for example, from 1 to 2. So, this is the interval which is the part of the real line, and the codomain is the real line. So, this is a function given by the formula f of x is equal to 1 for every x in the domain 1, 2. Let us try to draw a graph of this function. How would you draw the graph of this function? For every x, I should look at the ordered pair x comma f of x. F of x is equal to 1. That means, I should look at all ordered pairs x comma 1, x belonging to 1 to 2. But with the association, the ordered pairs x comma 1, what are these? So, these are points on the plane which lie on a line, on a horizontal line. Okay. So, what is that? So, a point between 1 and 2. If I take a point x here, what is f of x? F of x is a height 1. So, this is the point. So, this line segment is the graph of this constant function f 1 to 2 to r by given by f of x is equal to 1. So, this is the constant function, right, taking the value 1 everywhere, okay, on the domain which is 1 to 2. Okay. So, for this function, the domain is the interval 1 to 2, it is the open interval 1 to 2. So, what is the range? Range is the single point 1, right, range is a single point 1. Can you say this is 1 1? Obviously not, this is not 1 1 because all the points in the domain all get mapped onto the same value 1. So, this is a function which is not 1 1, right, and codomain is R. What is the range? The single point 1. So, this is also not onto. So, this is neither 1 1 nor onto. Okay. But it is a nice very simple function with a nice graph. So, the constant function f x is equal to 1 in this domain 1 to 2, this is the graph of it. Let us look at slightly more general example. Let us look at a function r to r given by the formula y is equal to f of x. It is m times x, where m is a fixed real number. So, what we are saying, every point x is related to y, where y is equal to m of x, right. We want to look at the graph of this function, what is the pictorial representation of this function. So, graph of this is the set x comma m of x, x comma y, where y is equal to f of x. So, the graph is x comma m of x, x belonging to real line. So, let us see these ordered pairs, how they get represented on the plane in terms of the coordinates that we have defined, right. So, using school geometry, we can visualize it as follows. First, let us note that the point 0 0 belongs to the graph. If x is 0 in the domain, then y is also 0 0. So, the point with coordinates 0 0 is on the graph of the function, right. Next, let us take 2 points p and q on the graph. So, the first point is with x coordinate x 1. So, what will be the y coordinate? M of x 1. Q is x 2. So, the y coordinate will be m of x 2, because that is the function f of x. So, given these 2 points, so these are 2 points. Let us take any general point x comma m x on the graph of the function. So, now this is the point P, which is x 1 m x 1. This is the point Q, which is m 2 x 2, m of x 2, y is m of x 2. So, and 0 0 is already on the graph. So, let us look at these 2 triangles OPA and OQB, or you can also look at the triangle PQC. So, let us look at this triangle POA and QPC. These 2 triangles are similar triangles, because this angle is 90, this angle is 90. This angle is equal to this angle, because this is a horizontal line I have drawn, this is a vertical line. So, these two angles are equal by the property of parallel lines and a transversal intersecting these two angles. So, these two triangles are similar. What does similarity of triangles means? Similarity of triangles says that the ratio of the corresponding sides are equal. So, P A by O A is same as Q C by P C, right. So, what is P A by O A? So, that is m x 1 divided by x 1, that is m, right, and m x 2, this point is m x 1. So, what is this height? That is m times x 2 minus x 1. This height is, this base is equal to m times x 2 minus x 1. So, that gives us the relations. That is not visible. So, let me write that. So, that gives us the relations m is equal to P A divided by O A, that is also equal to Q C divided by C P. This one is equal to m times x by x 1 by x 1, and this is equal to m times x 2 minus x 1, this is by x 2 minus x 1. So, all these are equal, right. So, what is m? M, if I take x 1 equal to 1, okay, then it is equal to P A if O A is equal to 1, right. So, that essentially what we are saying is, if I take any 2 points, right, then they are going to be on the same line, that is the red dotted line. So, the graph of this, because if I take any 2 points on that line, then the ratio is same. So, for every point x, if I take a point here, that is going to be the ratio is going to be same. So, that triangle is going to be same as similar to this triangle. So, all these points are going to lie on the line. So, that means that the equation of the, so that means the line y equal to m x will have graph as a line where if I take this distance as 1, right, this height will be equal to m. Okay. So, that is the property. So, that is the graph of, in general, if I take a function y equal to m x plus c, where m and c are fixed, then if c is 0, it is the original graph, and only what we are doing is we are changing the y value of y by adding c to it. So, it is just moving the graph of the original function by c units. If x is equal to 0, then y is equal to c. So, it passes through the point 0 comma c, and m remains the same, that inclination in a sense remains the same, it is parallel. So, that means if this is a line y equal to m x plus c, and if we just translate it and draw a parallel line, then this is the graph of the function y equal to m x plus c. This is so such functions are called linear functions. So, what we have done is we have looked at the concept of a relation, looked at the concept of a function. We have tried to discuss when is a relation called a function. Functions are normally given by formulas. We have tried to look at the graph of a function as a subset of the Cartesian product, and we have drawn the graph of a linear function y equal to m x plus c, and that turns out to be a line. And conversely, one can easily show, probably we will do it in the next lecture, that every line is the graph of a linear function. So, thank you.